Today I want to show you two more examples about good and bad methods. Then the second topic is section 101 from the first book. The first book. Yeah. When you take a look and I wrote at least 3 books. Yeah. Section 101 from the first book. About Taylor's field. Two more examples. Topic 1. Example 1. In this example, let's consider the computation of determinant of a matrix. Yeah, a matrix. N by N matrix. A1N, A21, A22, A2N, AN1, N2, N. Determinant of a matrix is a number. The notation is DET, determinant. Or, two popular notations for determinant. What is determinant? Determinant, if determinant is non-zero, the matrix is invertible, has inverse. If the determinant is 0, then the matrix has no inverse. How to compute determinant? We have a formula definition. Yeah. The first case, okay, case 1. The matrix, the size is 1 by 1 matrix. Then determinant of a 1 by 1 matrix is just the entry A1. A1. Now the second case, the size of the matrix greater than 1. Right? Case 2. N greater than 1. To introduce the formula to compute determinant, let me introduce 2 notations first. Okay. Let me let Aij be the submatrix obtained from A by delete row I and column J. By deleting row I and column J. N by N matrix, I delete row I, delete column J. I have N minus 1 by N minus 1 matrix. Yeah. I let Aij to denote that matrix, submatrix. This is our first notation. Yeah. First notation. Now, second notation. Second notation is second notation. I let Cij is a scalar, a number. Below this number, let the one I plus J. Then times determinant of Aij. Determinant is a number, so negative 1 to I plus j times determinant is a number. Cij is a number. Now, with these two notations, I can present the formula to compute determinant. Yeah. Now, the formula to compute determinant is then determinant of matrix A. Look at the first row of matrix A. First row, A11, A12, A13, A1n, right? First row of the matrix. Now, this formula expands determinant along the first row. A11 times C11. What is C11? Define it. Set I1, J1, you get C1. Plus second entry. A12 times C12 plus A13, C13, and so on. A1n, C1. This is the formula or definition of determinant. Yeah, let me show you two examples about how to use this formula. Okay, so example. For example, consider a small matrix. A11, A12, 2 by 2. Yeah. I want to compute determinant of this 2 by 2 matrix by formula. Right? Determinant by formula. Right? Formula here. Expand the determinant across row 1. So A11, C11 plus A12, C12. And what is C11? Right. Definition here. C11. Left is 1. 1 plus 1, right? I is 1, J is 1. Then times determinant A11. What is A11? Delete row 1, delete column 1 in the which is A. Right? Okay, let me write down the second term first, okay, before I delete row 1, column 1. Then plus A12 times C12. Then I to 1, J to 2. Negative 1, 1 plus 2, determinant of A12. And now let me simplify. Negative 1 to 1 plus 1, 1 plus 1 plus 1 is 2. Negative 1 squared, positive 1. So A11 determinant. A11. Right? How about here? Negative 1 to the third. Negative 1. So minus A12 determinant. A12. Okay, now what is capital A11? Which is A. Delete row 1, column 1, then the remaining A22. That is capital A11. Yeah. So this is a A11 determinant of this matrix, 1 by 1 matrix A22. Then minus A12. What is capital A12? Delete row 1. Delete column 2. A21. So this is a determinant A21. One by one matrix determinant is the entry itself. So let me continue here. Yeah. Here. Here. So I get A11, A22 minus A12, A21. Yeah. A 2 by 2 matrix determinant is a number. Determinant is A11 times A22, product of diagonal entries, minus A12, A21, A12, A21, product of anti-diagonal entries. So a 2 by 2 matrix determinant is product of diagonal entries minus product of anti-diagonal entry. Yeah, this is a first example about this formula. Second example, okay? Second example, okay? Example, one more example about this formula. Okay? About this formula. Okay? Take note. Okay? Compare the determinant of this matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 by 3 matrix. Okay, now let me compare. Okay. Formula. Okay. Now solution. Determinant of A. I expand the determinant along the first row. So first row A11, 1 times C11. Yeah, formula. Yeah. A11 times C11. Yeah. And then plus A12, number 2 times C12. Yeah. A12 times C12. And then plus A13 times C13. Yeah. Yeah. Formula. Okay, now what is C11? C11 is a 1 times, 1 times. C11 is a -1. I plus j, now 1 plus 1. Then determinant of capital A, 1, 1. Then plus 2 times C12, -1 to 1 plus 2, determinant of capital A12. And then plus number 3, -1, 1 plus 3, determinant A13, right? Yeah, before I compute determinant of capital A, simplify the expression. Yeah, -1 square, -1 to the second is +1. Okay, so this is just a determinant A11. How about here? -1 to the third, negative. So -2 determinant A12. Then plus -1 to the fourth, positive. Uh, now, simple A11, delete row 1, column 1. So determinant. So it is a second popular notation is a vertical line. Okay, delete row 1, column 1. So 5, 6, 8, 9. Okay, yeah, vertical line. Determinant. Minus 2. Capital A12. Delete row 1, column 2. So 4, 5, 7, 9. Now, number 3. Capital A13. Delete row 1, column B. So 4, 5, 7, 8. Yeah. And now 2 by 2 determinant according to previous example. Product of the main diagonal entry 5 times line minus product of anti-diagonal entry. Yeah. This is the determinant of this 2 by 2 matrix. 2 by 2 determinant. Okay. Then minus 2 times product of the main diagonal entries minus product of anti-diagonal entries. And then plus 6. 4 times 8 minus 7 times. Then calculator. We have it happens still. This matrix determinant is here. That means that this matrix has no inverse. A matrix has no inverse. We also say that the matrix is singular. Singular. Non-singular matrix has inverse. Singular has no inverse. Has no inverse. Okay. Now, this is the formula to compute determinant. Now, let me show you the computational course about this formula. Yeah. Yeah. In general, computing an n by n determinant by, let me give a name to this formula. Yeah. Say I call this formula star. Computing an n by n determinant by star. Computational course requires about, not exactly, about n minus 1 times n factorial. Yeah. So many multiplications multiplication. If you use this formula to get n by n determinant, how many floating point multiplications you need to perform? So this is a very huge number. Say for example, very huge number. Suppose we want to compute a 20 by 20 determinant. Yeah. Very small size determinant, 20 by 20. If you know, enter this determinant into your calculator. Some calculator can solve matrix problems. If you enter a 20 by 20 determinant to your calculator almost immediately gives you the answer. But of course, your calculator doesn't use this formula to find the answer. Suppose here, I use this formula to find the answer. Let's see how much time we need to wait for the result. Okay, yeah, yeah. 10 by 20 determinant multiplication. Yeah, only consider multiplication. How many? 20 minus 1 times 20 factorial. Factorial, okay? This is 20 factorial. Yeah. Suppose I have a super computer. Okay? Yeah. Super computer. Yeah. Super computer. This computer very fast. Per second, how many floating point operations? Say for example, 10 to 10 floating point operations per second. Okay, very fast. I use these supercomputers to find a 20 by 20 determinant. Let me see how much time we need to wait. Okay, how long? Okay. Time. Okay. You wait so many operations we need to compute. So 20 minus 1 over times 20 factorial over 10 to 10. So many seconds we need to wait. Okay? Make sense, right? Hey, 1 hour has 3,600 seconds. So how many hours? Calculator. 1, 2, 8, 4, 0, 31 on 62 hours. Okay? A day has 24 hours. How many days? 5, 3, 5, 0, 1. 32 days. A year has 365 days. How many years? 146. About, okay? 0.5. 8 years. If you compute just a 20 by 20 determinant by using this supercomputer, by this method, you need to wait over 100 years. Clearly, this approach is a bad method. Even though you have the final answer, we don't trust the final answer because so many floating point operations involved. how much round of error, how many round of errors involved. A lot. Okay, we don't trust the pilot. But when you enter 10 by 20 determinant into your calculator, just take less than 1 second, you get the answer. Why? Because your calculator uses a good method. So clearly, this is a bad method. A second example about bad method. Okay, here. One more. Yes, the last example. Example 2. Stop a linear system. A is n by n. A B, right hand side, is a vector, n vector. The vector has n entries. A typical solution for solving a linear system is Gaussian elimination. Okay? Yeah. Gaussian elimination, popular. Yeah. GE, Gaussian elimination is popular. In matrix language, GE, Gaussian elimination is step 1. Compute LU factorization on matrix A. What is L? L, a lower triangular matrix. U, upper triangular matrix. U, upper triangular. Step 1. Now, step 2. AX is B. Now I have L and U. I put L and U into A. LU X is B. Yeah. X, I don't know. I want to find X. Now, let me U times X. Let me denote it by 1. Okay. I don't know X. I want to find X. So I don't know Y. Okay. Now, so L times Y is B for Y. Okay, for Y. Yeah. Okay. Remember, L is lower triangular matrix. How to solve this linear system? Forward substitution. Yeah. So this step is cheap. Okay, compared to the original linear system, to get solution X, computational cost is order n cube. Lower triangular matrix is a lower triangular linear system. The solution for Y is order n squared. So Y order less, much faster. That's why we compute LU frequency. After we get Y, then UX is equal to Y. Solve this for X. Then solve is equation for x to get x. Right? U is an upper triangular matrix. So this linear system, how to solve it? Backward substitution. It is cheap. Computational cost is only order n squared. Okay. So yeah. After we get LU factorization, then this whole step 2 is very fast to get the answer. Popular notation. A popular solution, Gaussian elimination. Now, but in industry, people usually don't use this solution to solve this approach to solve linear system. Why? When matrix A is large, what it means? Large. The size is large. How large? 10 billion. Billion, okay, in industry, okay. Because linear systems are usually from discretization of differential equations. When matrix size larger, the solution to the differential equations more accurate. So usually it's common now because we have supercomputers, 10 billion size, 10 billion by 10 billion. This is very normal. When A is large and sparse, a matrix is sparse. What it means? Most of the entries are zero. Sparse. Most of the entries are non-zero, then we call the matrix dense matrix. Dense. Sparse. When matrix A is large and sparse, the storage of such a matrix A is cheap. We just need to store the non-zero entries. Most of the entries are zeros. We don't need to store zero. We only store non-zero entries. So cheap. Even though the matrix size is 10 billion, it doesn't matter. Okay? Cheap. However, okay, when you compute LU factorization, even though matrix A is sparse, but L and U, they are dense. Okay, yeah, L. Dense, okay. Most of entries non-zero. Yeah, U, upper triangle. Yeah, most of the entries are non-zero. Right? In this case, if you still use CE to solve the linear system, okay, compute LU factorization, then keep L and U. Because we need L and U in step 2. So we need to keep L and U. How to keep? Hold them in memory. Right? L and U, dense. Use them dense. Right? So L and U together, there are n squared, so many entries. Do you get? my computer need to the hold L and hold U together. So many non-zero entries I need to hold. And imagine very large, 10 billion, n squared. This is okay. I don't think I think low computer, even supercomputer, cannot hold such a big number of such a big number of data. So when we should say it's large and sparse, people in industry don't use GE to solve things. Use iterative method to solve these things. Because storage, easy storage. Yeah, this is a bad method. GE, Gaussian distribution. Yeah. In this case, large and sparse. People don't use GE to solve these. Yeah, I think with this example, I finished the introduction of the topic of good and bad methods. Okay, now the second topic today, we turn to section 1.1 in the first book. Taylor's theorem. We often use Taylor's theorem in this class. Second topic today. Taylor's theorem. Yeah. Yeah, maybe you have learned this theorem before, right? Yeah, if you are math background. Okay. Yeah. Taylor's theorem. There are at least two forms for this theorem. The first form, okay, theorem, Taylor's theorem. Before I present this theorem, let me introduce a location. Yeah. Let me let C means continuous. AB open interval. Okay. I use this location below the set of all functions. Say n, f of x. Okay. These functions define on the open interval AB with derivatives. First derivative, second derivative, third derivative, and so on until n derivative. Yeah, this n. Yeah. If n is 3, first derivative, second derivative, third derivative. With all derivatives, existing and being continuous on AB. Say for example, yeah. For example, sine is finite. This function should be inside this set. This function, you can take derivative as many times as you want. Derivatives all continuous. And this function actually defined from negative infinity to positive infinity. So this function is in this set. This set is the function defined on AP and derivative up to order n, all continuous. And being continuous. All right, now with this location, I can present Taylor's theorem. This theorem has at least two forms. And Taylor's if function f is from the set, say n plus 1, AB. Yeah. N plus 1, take derivative up to n plus 1 times. All the derivatives are continuous on AB. Then, for any points, for any 2 points, C and X from in the open interval. Yeah. C usually constant, X variable. C and X from this interval. We have f of X is equal to f C. C usually a constant, so fc a constant plus 1 over 1 factorial f derivative c, because f is from the set derivative exists and continues times x minus c plus 1 minus 1 over 2 factorial second derivative is c x minus c squared plus okay. First term, second term, okay, then plus 1 over n factorial n c x minus. About this equation, left hand side is a general function. Right side, constant x minus c, constant x minus c squared. So actually, the right side is a polynomial of degree n. Left side, a general function. Right side is a polynomial. To make them equal, you need to add one more term. Difference. Error term. Okay, we call it error term. Error term. Yeah. Left side, a general function. Right side, polynomial. To make them equal, add an error term. Then, what is the error term? The formula is where the error term, right, is the formula 1 over n plus 1 factorial and derivative n plus 1 times. Because I assume this f from this set, by definition of this set, function f has derivative up to n plus 1 times. So this is derivative n plus 1, then evaluate at some point sine times x minus c n plus 1. Then what is sine? Where sine is a point between c and x. Exactly what sine is, we don't know. But we know sine this one depends on c and x, and also between c and x. Yeah, that's the point. So Taylor's theorem says that general function can be approximated by a polynomial. The error given by this formula. Yeah, this formula. Yeah, Taylor's theorem has two forms. Yeah, error in this form is called, yeah, the error is called Lagrange. Lagrange. And no, Lagrange. Remainder, okay? Remainder. Lagrange error or Lagrange remainder. We have second form, but not today. Okay? So today I just present this field. We often use this field from the beginning to end. So take at home, study my notes. Okay? Try to understand this formula. Actually, essentially, basically, this formula says that left side a general function, right side polynomial. We use polynomial to approximate a general function. Error is given by this formula. Sine, we don't know. We just know it is between c and x. And depends on c and x. Different c, different x, this point different.